30 different contestants who started off in SDN Idol. The judges have narrowed it down to a group of 4, and now it's your turn to choose the winners. So there's a couple different criteria we'd like you to think about when the presenters go through their demonstrations. So number 1, the technology value. Number 2, the business value. Number 3, the differentiation versus other things that you might be aware of. And then finally, how this product or this demo advances the state of software-defined networking. So we have 4 exciting demonstrations. Don't hesitate to ask questions, although do let them get through the presentation. They'll go for about 20 minutes, and then you'll have free reign for about 3 to 5 minutes. So with no further ado, I'd like to welcome Huawei on their discussion of IP and optical synergy.
I'm really glad I don't have to sing. That's all I can say. First of all, thank you, and we're very pleased to be bringing our SDN Idol demo here for you today. Our customers, our carrier customers, tell us a number of problems that they have over and over again. We hear them talking about the cost of the operational costs of their network, all of the sort of clickety-click and so forth that has to go on. They talk about the cost of the equipment and trying to reduce those costs, and they talk about the costs of introducing new services. So our SDN demonstration here is going to address directly our customers, our carrier customers' requirements by showing how we can actually integrate the operation, control, and management of what were previously 2 completely separate networks, the IP network, of course, and the optical network. We're going to see 3 demonstrations here. We're going to demonstrate IP link deployment from a very simple centralized orchestration system, which will configure the IP layer and the optical layer simultaneously. Then we're going to step it up a little, and we're going to look at a service-driven topology optimization, which basically means that when a service comes up in IP, the optical layer is going to react to the bandwidth demands that come from that new service, and react more or less instantly. And then we're going to look at a couple of new forms of restoration that can be done when you have a hybrid view of the IP and optical layer. Could you please advance to the next slide? So just a quick overview of what we have in terms of this technical solution. Of course, we have an optical network, and I'll talk about that in a few minutes. And the optical network is controlled by an SDN, a transport SDN controller. We have an IP network being controlled by an IP SDN controller. And then above both of those, you can think of it as a sophisticated application, as an orchestration system, which consolidates the views and consolidates the management and operations of these 2 networks. There are some ancillary devices in here which we're not really going to cover, but are of course required in a large service provider network. The main messages here are the ability to produce a converged view of the network and a converged multi-layer network, resource visibility, debugging capability, which is anybody that's debugged an IP or an optical network or tried to do them at the same time knows what a boon it is to be able to see all of the bits and pieces simultaneously. Automation, the interaction between the IP and the MPLS and optical layers is another major component that you will see in the demonstration. You're going to see multi-layer optimization and an intelligent traffic engineering that looks at the optical layer while it's doing IP MPLS TE routing. And then, of course, a new availability mechanism, which we'll go through. Could you please advance to the next slide? So in terms of the environment, it's a pretty sophisticated environment. Obviously, we couldn't bring it here. It consists of about 6 or 7 racks full of equipment. There are 6 routers, 2 of our smaller PE routers, which are dual-homed into 2 of our larger P routers on each side, making 6. And they're physically fibered to those P routers. And then we have physical fibers between the P routers and our OTN switches, right? The OTN switches are colored interfaces into our ROADMs, and so of course this is where the DWDM optical network begins. And with that, if you look at that configuration, we pretty much can configure the router connectivity any way we want automatically. And then we have an Ixia tester that allows us to put some traffic through. Of course, there's a series of servers off on the right-hand side running the SDN, the two SDN controllers, and the orchestration system through an out-of-band DCN network. The other thing that you'll notice here of interest is that you see the version numbers on those software. Those are product version codes. So this is available product now. So let's move on to the first demo slide. So the first demo slide, essentially what we're going to do, you can see the starting configuration of the network. There are no links between the routers except for the physical connectivity between the PEs and the Ps. So what we're going to do is we're going to choose from a set of possible but not currently instantiated optical connections, and we're going to instantiate two of them. And at the same time, we're going to take a look at the topology. While we do so, we're going to look at it from the IP view, we're going to look at it from the optical view, and see things simultaneously from the orchestration system. So let's go ahead and, if you wouldn't mind going through the first portion of the live demo. So now we're going to switch to view. This is our orchestration system. What you're looking at is the orchestration system's view that it's brought up from the IP controller and the SDN controller. This is the fiber view. So we're going to go through, and we're going to now look at the optical view, and we're going to look at the IP link view. So you can see the three different views, and then now we're going to show this multi-layer view, and this will give us a sort of a three-dimensional representation of all of these layers. Again, this is live, real equipment in Beijing. All right. So now we're going to look at the basic resources that we have available here in the network. First thing, we see the controllers, the IP controller and the transport SDN controller. And now we're going to go and look at available virtual links that the IP could be used by the IP topology. And we're going to select two of these. We're just going to interconnect the P routers at the edges. So he's going to activate that, and then we'll go through the views here again. All right. And as soon as this refreshes, we should see that the optical layer has created the connectivity. So we got a new DWDM connection, an OTN connection, and then the routers were configured with the appropriate adjacencies to create those links. And we can look at this multi-layer. And here we see, we can't change the speed of light. SDN is good at a lot of things, but 16 hops to Beijing. And here we see the OTN layer connections, the DWDM layer connections that were created, and of course the IP connectivity. So we're seeing all of this thanks to the orchestration system, which is gathering up the information from the two layers below. All right, so let's move on to the next demonstration. The next demonstration, essentially what we're going to do is we're going to create a service. Well, we're going to create an RSVPT connection, a bidirectional tunnel between PE1 and PE2, but in this particular scenario, there's no bandwidth available between PE1 and PE2. But what's going to happen is that the optical layer is going to be triggered to create the appropriate bandwidth. So in other words, the IP service creation through RSVPT is going to end up triggering the SDN controller on the optical side to create the appropriate connectivity between P1 and P2. So let's go ahead and do this, step through this demo. So here's our existing topology. What he's doing now is he's going into the orchestration system and configuring the first of the two bidirectional tunnels. He's configuring an 8 gig connection between PE1 and PE2, and he's going to apply that. That's pretty much all he has to do. And all of the rest of the magic is taken care of by the pair of SDN controllers in the orchestrator. So we're going to now take a look at the what's actually happened here. So here we're looking at the IP link layer view. As soon as that refreshes, we should see a new link between A and B. And there's our link between A and B. So that link was triggered as a result of an RSVP connection setup. Previously didn't exist. Let's take a look at the service view here. And we can see the one tunnel. And we'll look at the multi-layer view of this service. And now we'll see the 4-layer, I believe it is, view. Right? All the way at the very bottom, we see the fiber connectivity that's a portion of this service. We see the OCH TDM layer. Then we see the IP link layer. And then we see the tunnel layer, all in one view. All right. Now I believe the next step is configuration of the reverse tunnel. Again, 8 gig, PE2 to PE1. Activate that, and then that service will come up. So at this point, we have 2 bidirectional tunnels created, and we can see the 2 services, and we can look at the multi-layer view of the second service as well. Again, we can see all 4 layers simultaneously. Fiber layer, the OTN layer, the links that make up the hops from the MPLS TE tunnel layer, and then the point-to-point for the TE tunnel. Okay, let's move on. Right on time. Okay, well now we're going to look at probably the most interesting portion of this demonstration, which is the multi-layer restoration. In order to do this, like every good IP or data demonstration, we need a data source. What we're going to do is we're going to create an L3 VPN on PE1 and PE2. We're going to put traffic on that L3 VPN, and the L3 VPN is going to be mapped to the bidirectional tunnels that we just previously created. And then we're going to do what every good demonstration does, is we're going to cut the fiber between the OTN1 and the OTN3 attached ROADMs, and that will cause the optical layer to compute a new path and to restore the IP link without IP knowing about it, and that's fine. But the most interesting one is when we do the second break. We're going to take the fiber, the last remaining fiber that would get us to that OTN3 device, which would get us to P2. We're going to break that. And what's going to happen then is the optical layer is not going to be able to recover that particular IP link. And then what's going to happen is the IP layer is going to do a recomputation, and the IP layer is going to discover the fact that it could get there if it had a connection between OTN1 and OTN4. And then it could route to PE2 that way. So it's actually going to, the IP layer, when it reroutes, is going to cause a new link to be created between OTN1 and OTN4. All right, so let's go ahead and go through this demo. All right, so the first step is the creation of the VRFs. So through the first controller, the IP controller, we're configuring an L3 VPN and associating it with the tunnel pair. I'll just let him go through that. And putting an IP address on an incoming port, and that'll be associated with the IXIA. Okay, that's been activated. Now we take a look at the service, our L3 VPN service. Okay, keep going. And we're looking at the multi-layer view of this L3 VPN service. So now we're looking at all 5 layers simultaneously. So at the very top, there's our PE1, PE2 VRF. There's underneath it is the tunnel, and then underneath that, the IP connectivity. Underneath that, the OTN, and then underneath the fiber connectivity. So you're looking at all simultaneously from the service all the way down to the fibers that it traverses all in one view. Well, the next step is a failure. So this is the Ixia showing the traffic starting to flow. That green line, of course, is the traffic starting to flow at the point when he created the L3 VPN. He's now going to fail the fiber. So somebody's running into the lab right now in Beijing and pulling on a wire. And we will see a brief interruption while the optical layer recovers the IP link. There it is. Okay. And I believe now we're going to take a look at the results from the ONM view. So this will refresh. This is the fiber level view, and you can see that fiber is down. Now we take a look at this from the service level, and we'll look at the multi-level view of this service. And we'll see that the IP layers haven't changed, but the IP link, if you look at the IP link, the second level there, it's been rerouted via that sort of dogleg optical connection there. So that's sort of pretty much what you'd expect from an optical control plane to automatically recover that. But it gets more interesting. So now what we're going to do is we're going to fail the other fiber, which is going to make it impossible for the optical layer to recover this connection to that P router. So now it's going to take a little bit longer because we actually have to bring up a new link. What's happening is that the optical layer said, I can't do that. IP, it's gone back to IP, and the RSVPT is trying to find a new connection. It's looking at its database, which has been given to it by our SDN controller that gives it lots of available optical links that it could use, but that are currently not instantiated, and it has computed one. And in the process of setting that up, it has actually instantiated it. So there we go. We've now recovered the IP layer by instantiating an optical connection in response to an IP layer routing or rerouting request. And we can take a look now at the end fiber connectivity. We can see when this refreshes, we'll see the two fiber breaks. There we go. So you can see that's the remaining IP links. And we're going to look at this from a service level view and a multi-layer view of the service. And now what we're going to see is that the correction has been made, the recovery has been made at the IP layer, creating that new OTN and DWDM connection underneath. Again, all because this is all possible because we have the SDN view of the optical network, the SDN view of the IP network, and we're able to operate them both simultaneously through the orchestration system. So just in summary, what you've seen is a converged view. You're looking at it right now, a converged view of the IP network and the optical network, the ability to configure, provision, and monitor and watch what's going on. You've seen an automated system that allows the IP and MPLS layer to automatically trigger actions on behalf of the optical network underneath, and also services above IP automatically and sort of recursively triggering that because of a pair of SDN controllers, an orchestration system, and the northbound APIs that allows. There's a degree of multi-layer optimization that's happening here. As part of the computations, the PE is being given paths that are available in the optical layer and allowing us to do essentially a multi-layer optimization. And we've also demonstrated an availability mechanism where in response to a failure, the IP layer has actually caused the triggering of an optical layer connection. That's the end of the demonstration. What I would like to point out is that in the exhibition hall at the Huawei booth, and in fact, I believe there are some others also talking about it, there are multi-vendor demonstrations that are somewhat similar or actually very similar architecture to this. showing IP and optical synergy, and we certainly hope that you pop over there and take a look at them. That's it for me. I've got 23 seconds left. I guess I've got 22 seconds for questions.
Thank you, Peter. If you do have a question, please come on up. But while you guys are formulating your question, I want to ask you, can you characterize versus what the state of the art is today? What's the business value in terms of time, money, or any other metric that you think this technology confers?
Sure. Well, I mean, today, a service provider's optical network is managed by a different group of people than manage the IP network. So if you want to do something that involves the two networks, you pretty much have to have a human communication. There's usually a paper trail. It's a lengthy, time-consuming process, and some of our customers talk about days and days, maybe even longer, to get something that the IP group wants to happen at the optical layer. So there's this whole human interaction thing that we've just shown you. SDN has removed a bunch of humans from the process. So the moment you get rid of a person from the process, you make it less expensive, less error prone, and in generally just an easier system to deal with. There's still human, you still as a human have an oversight and an overview of what's going on. So you're not losing control of the network, but you have that control of the entire network, all the things that are happening simultaneously. So this is a very different way of doing things, a better way of doing things, and it comes about because of the logically centralized control that SDN affords us.
Great. Thank you, Peter. Okay, so our next contestant is Cavium, and they're going to talk about their X-Pliant switch. Please come on up, Cavium.
So first of all, I want to thank everyone for giving us the opportunity to compete here today and be one of the finalists. A lot of great products here, a lot of really interesting products, and that last demo was really cool, a lot of really cool stuff. So being part of SDN, I mean, who loves SDN? Anybody? Yeah. If you're in networking today, you might as well be part of SDN, right? I mean, this is where all the exciting things are happening. This is where the shift and the changes are going to happen, and this is where all the new ideas are really happening in networking, and this is the best place to be. So, you know, if you think about all the things that we see today, there's silicon, there's systems, there's software that rides on top of that. So at Cavium, we're the silicon. And our silicon, our X-Pliant silicon, is designed for SDN. We're really the first chip to come out that's a high-speed, high-throughput switch designed specifically for SDN. That's what we're going to talk about today. We put out a press release this morning talking about what we're doing. And in our press release, really what we're mentioning is that we now have integrated native OVS software onto our X-Pliant switch. And we can get dropped into a network and talk directly to an OpenFlow controller. And so the demos that you're going to see today are all based on that. It's all based on open source, open software in order to do that. To give you an idea of where we're at, I mean, X-Pliant is really about combining the highest level of throughput with the highest level of flexibility. And in the old days of networking, there's a lot of switches that are available today, a lot of silicon that's available today based off of architectures that aren't very flexible. They have fixed pipeline, and people are, you know, doing some cool SDN stuff with it, but still not really allowing you to unleash the complete level of flexibility and power to take control of the network. Alternative architectures just aren't fast enough. Network processors, FPGAs, for example, to achieve these level of throughputs. What we have today is a monolithic silicon, goes up to 3.2 terabits per second in a single chip, supporting all these speeds from 1 gig all the way up to 100 gig, including the newly released 25 gig specification. We have a complete software kit that goes with that. And what we're going to show is we have different profiles that run on the chip. And you're going to see a couple different profiles today. You're going to see a pure OpenFlow profile, and you're going to see a hybrid OpenFlow profile where we have a standard layer 2, layer 3 profile combined with an OpenFlow profile. We see people have a lot of interest in saying, I want to run my network the way that it's running today, either layer 2 or layer 3 or the combination, but I want to slowly start introducing OpenFlow and maybe introduce OpenFlow to start taking care of the control plane and other types of special packets. How can I do that without being disruptive to my current network topology? So we're going to show you that as well. And we have lots of cool stuff. I mean, from an SDK, we're all about open source. We're all about supporting the software abstraction interface and enabling it to be easy to use. A lot of benefits of this: protocol independent programmable switch. This is what we are. We're protocol independent. The switch can do any protocols, any overlays, anything that you'd like to do. Today in OpenFlow, OFDPA, you're really restricted to these very specific table type patterns. It's very restrictive in what you could do. In our switch, you can create your own TTPs, and we're going to show you in a demo how you can do that today. And as well as the fact that we're very flexible from tables. You want to build just gigantic OpenFlow flow tables, you can do that. You want to mix that with layer 2 and layer 3 tables at the same time, you can do that as well. It's just one huge table. You can carve it up any way you'd like to carve it up. So what we're going to show, first I'm going to show you essentially kind of how our architecture works. I'll show you how OpenFlow is mapped to that architecture. I'll show you how hybrid OpenFlow is mapped to that architecture. And then we'll show you the OpenFlow demo and the hybrid OpenFlow demo. So essentially this is how our switch works. We have a programmable parser, and we have a number of these lookup and decision engines. Then we have big pools of memory that you can use, that the lookup and decision engines can use. You can program your parser, and this is, I'll use an example of a basic top-of-rack switch. You could program your parser with any sorts of fields you want to pull out. You can grab any parts of the packet. You can look at any parts of the packet. You can start feeding those to these different lookup and decision engines. And for example, if we want to start by looking at tunneling, we can decide how much memory do we want to use, how big do we want to make that tunneling table. Next, we may want to have a policy table. How big do we want to make that? Next, we may want to do layer 2 bridging. How big would we like to make that table? And then finally, layer 3 bridging and rewriting the layer 3 routing, rewriting the packet. So these table sizes can be allocated any way you like. Now, as we go to the demo today and we go to OpenFlow, the OpenFlow pipeline really is just a number of cascaded lookups. And in our architecture, we have the flexibility. We can do a lookup. We can take the result of that lookup and use it in the next lookup. Okay, so essentially what we'll do today is we have a chain of OpenFlow tables, and we'll be identifying flows with these OpenFlow tables and steering them, and we'll be modifying those flows as we steer them as well. So this is a pure OpenFlow pipeline. Now, for people that aren't as daring to go directly to a pure SDN network and they want to use a layer 2, layer 3 network and put some pieces of SDN on top of that, we've created the hybrid OpenFlow pipeline, where you see typically the same layer 2, layer 3 and tunneling capabilities that I showed in the original slide. But this time, in parallel with that, we put a number of SDN tables and OpenFlow dedicated tables. And these OpenFlow tables, we have the ability to go through the OpenFlow tables, go through the layer 2, layer 3 tables, all in a single pass. So that's really performance. We have the ability to do that without having to reroute packets. We don't have to play any fancy games with that. Very simple, very straightforward to achieve high levels of throughput. So first demo on the top slide will be a pure OpenFlow demo. Second demo will be a hybrid OpenFlow demo. One thing that's really cool is that all the software that you're seeing today and everything that you see is open source. Everything's available in open source. We use a Postman client. We write our commands in XML. We send those XML down to an Open Daylight controller. That Open Daylight controller is controlling the network, which in turn sends those commands based on OpenFlow 1.3 down to our switch. We have Open vSwitch integrated on the switch, takes those commands in, modifies the tables, and then obviously the packets are sent through the switch and accelerated in hardware. Okay, so everything's open source. So the first demo is very basic. You'll see traffic steering of a video stream. We have a video stream that's going into our X-Pliant switch. We have the Open Daylight controller on the side. And we'll be steering the video stream to laptop A. And then we'll come in, we'll enter some commands in the Postman, send it down to the Open Daylight controller, send it down to our Open vSwitch, and we will rewrite destination IP address and steer it to host B. So some basically policy-based routing. And we can do this at very large scalability. Second demo will be a hybrid OpenFlow. In this demo, again, how I showed, we have the OpenFlow pipeline and we have the layer 2, layer 3 pipeline at the same time. You'll see we'll be sending traffic we'll be using a Spirent tester in this case, where you'll see the traffic showing up on the Spirent tester port 1. We'll then go in, we'll send a command that will go through, it'll change the MAC DA and then the packet with a new MAC DA will flow through the standard layer 2, layer 3 pipeline and be switched out of port 2. So these are 2 demos that you'll see today. So I'm going to pass it off to Alec here, who can go now show the demos.
Thanks, Eric.
To see all the concepts that you see applied here to OpenFlow can also be applied to any sort of tunneling capabilities. So people that are interested in doing things like VXLAN or the newly released Genève protocol, we support those protocols. In these same demos, we can do routing in and out of those tunnels. We can gateway from VLAN tunnels to VXLAN tunnels and modify the inner packets and route those packets. So you can come see some of the other demos that we have as well in our suite. Please.
Yeah, thanks, Eric. So as the ONS says, define protocols and embrace open software. And this is basically what is our product about. The flexibility of our chip truly allows for SDN applications to define new protocols. You can match on almost any byte, any bit of packet headers. You can implement your own forwarding, paradigm forwarding schemes, or you can merge OpenFlow implementations into the traditional pipelines. And embracing open software, our chip can be managed from Open Daylight as well as from any other controller. So as Eric explained before, the way we are going to demonstrate this, the ways that application can actually control our switch and implement its own forwarding decisions and rewrite some packet fields is through a streaming of the video, applying rules from Open Daylight controller that will actually control the video stream. So you can see here we have the Open Daylight controller running remotely. And the rules are written here in XML. We are using just a plugin to a Chrome that sends this XML file to the controller, and controller maintains its states and actually loads specific rules to the switch, and we just execute this command. So currently we will match on the video stream, incoming video stream, and we will reroute it to a different, we have 2 laptops in our lab. So we are matching on this flow. And actually, control to which laptop it will go. So the video appears now on laptop A. Sorry for the quality. Unfortunately, the network is not as fast as our chips. So the video goes to this one, and let's say the controller wants now to send it to a different hop. So we're just applying another rule. And in a second, there's some lag the video. Yeah, you can see it goes to the other, to the laptop B. So similarly, instead of tracking steering, obviously application can do more sophisticated implementations of forwarding schemes as well as modifying of the packet itself. We can also do a hybrid mode, which means that application may still rely on the existing layer 2 and layer 3 pipeline protocols, but still touch very specific flows that are of special interest for application, modify these packets, and then these packets will be processed within the standard pipeline based on these software-defined modifications. So we'll send another rule, and in this rule, we match on exactly the same stream. We change MAC destination address of that packet, and that packet is forwarded to a known address that is associated with this MAC address. So you can see we hooked up aspiring here, so you can see that the packets are going to this port, and we can modify another MAC address that has been automatically learned, and the packet will go to the other port. Yeah, you can see. So actually we demonstrate here that our switch can be controlled from the standard open source software from any controller. In this particular case, it's Open Daylight. The controller can fully control what happens to the packet, as well as merge these decisions into the regular pipeline.
So we've got about 5 minutes left. Are there any questions?
Once again, please come on up if you have a question. I'm going to lead with a similar question to the one that I have for the previous group. Can you talk about the use case where this reprogrammability, this reconfigurability is most impactful? And what I mean by that is that consumer networks, is that something to deal with video delivery, or maybe some other area? And if you could put some numbers.
Yeah. So the target markets for us are starting inside the data center itself. So typically what we've seen is people building large data centers out of large layer 3 ECMP networks, but still not really having the control to be able to move around virtual machines the way they may like to. And that's where a lot of these overlays are coming from. So our target market in the data center allows us to take advantage of the high throughput that we have. So very fast speeds for top of racks and core switches, but the flexibility to enable control and being able to move machines around the way that you'd like to, the ability to steer traffic the way you'd like to, and be able to take control. We also see a lot of applications in inter-data center traffic. So the WAN port between mega data centers, being able to create custom tunnels and steer those packets across those tunnels.
All right, so we have our first question here.
Hello. Just a question about the rate at which rules can be installed. Many years ago, I was always grumbling to our ASIC designers because they would give us lots of throughput in terms of packet throughput. But then when it came time for the control plane to install 10, 20,000 rules, it was always too slow in my opinion anyway. What kind of rates can we expect?
Yeah, I don't have the metrics off the top of my head, unfortunately, but I'll tell you that we do have accelerated mechanisms in there for doing tables. So we have a dedicated processor that's embedded inside the chip that allows us to essentially do batch table offloads back and forth. So we can talk to that processor. That processor can then go program those tables or do things in the background to offload the main CPU and expedite those tables.
Thank you.
So we can follow up with you later on, Peter, on the exact speeds.
Sure.
Quick question when you said any controllers. So I imagine it works with ONOS and also Ryu.
So currently we have tried the Flight Light and the Open Data, but there is no reason that it will not work with any other controller. We support on our side, standard OpenFlow communication channel protocol, so it will work with anyone.
Yeah, if it works with Flight Light, it'll probably work with the others. Thank you.
There's no tweaks.
That's a good demo. So one question is, like, say, in your slide, you mentioned about you could dynamic generate the parsing and then put in the profile so you can classify the traffic not based on the protocol. So I try to understand, like, which means you dynamically programming this in your hardware, or this is like some kind of pre-selected profile. Then the second question is, like, say, you could carve in the TCANs. So I want to see that how big is your total TCAN size and what's the key size that normally you're using.
Sure. So let me address those. I got short memory, so maybe I'll address the second one first. So you asked what size is the TCAM. We have both SRAM and TCAM inside the device, and historically it sounds like you're used to using some of the legacy silicon that's available today, where the only place that you could put rules is in the TCAM. Okay, and that's very limiting. In our architecture, you could put rules in TCAM. You could also put rules in the SRAM. And the fact that you could put rules in the SRAM gives us this very large scalability, and it's scalability in the hundreds of thousands of rules. Okay, key sizes will range anywhere up to maybe 256-bit keys. On the parsing side, we can parse any part of the packet, and what I was showing there as far as programming the parser and programming the LDE, the typical use case is that you will write these programs ahead of time, and you'll load these programs into the switch at boot up. So you have a little prom that'll load into the switch at boot up. That essentially gives the switch its personality, and it knows what it wants to look up and what it wants to do. Essentially knows what it wants to be. When the switch boots up without a profile, it doesn't know it's a switch. It doesn't know anything about layer 2, layer 3. It doesn't know about grabbing the inner packet of some MPLS tunnel. It doesn't know anything like that. So that's what really programming it does, and that's what the typical use case is, to get that done up front. But if you do want to change things in the field, you have the ability to go and change things in the field as well.
Okay. Thank you, Eric. Thank you, Cavium.
Thank you.
Okay, our next contestant is NEC, and what they're going to talk about is defending against cyber attacks with SDN. Thank you.
Great. How's everyone doing? Good afternoon. My name is Don Clark. I'm Director of Business Development for NEC. I want to thank the judges for their time and looking after us. We appreciate the opportunity to talk to you about what we're doing today with security in SDN. So NEC has been an early leader in software-defined networks. We have over 250 systems installed today. We have a lot of experience in deploying these networks. It started what we would think is phase one with this network control layer using OpenFlow. And that allowed us to create these simple systems like the one Cavium just demonstrated, and expose a single control layer that allows us to manage that entire network. What we see in phase two, what NEC brought to the table was network virtualization. That is the ability to abstract the network and to be able to use the network abstraction as the place where layer 2, layer 3 services get integrated. And then today, with the demonstration we're going to show, we'll show you how policy can be applied to that network virtualization model, so that we move to the next phase of SDN, where we're actually pushing policy into a virtualized network. The reason why we focused on the security and advanced persistent threats is because it's so in the news and such a huge requirement for our customers today. As everyone knows, security breaches have become very prevalent. There were 85 million announced records being tallied from intruders in networks. And the perimeter defense is insufficient to detect these spread of attacks. So we have the ability to defend at the perimeter, but once the malware is inside the network, they can use the social and ecological means to spread that malware across the network. And the organizational processes for defending against these, that is the approvals, the policies to defend against malware attacks, often slow the response down. So what we're going to show today is an integration of software-defined networking and security. And the benefits of this is that we can protect beyond the perimeter, so we can enforce that policy beyond just the firewall. We can take immediate action because we have that centralized control. Now we can move across the network. And we can have a consistent policy, not just to the most important assets of the network, but all across the network, so that the most vulnerable pieces of the network also get the same level of protection. NEC has been the forefront in both OpenFlow switching and SDN control. We're now on version 6 of our product. What customers love about our product is that they get all of the features of SDN, simpler, more responsive, faster, with no disadvantages. In other words, we have higher levels of availability, more programmability, more security than you get in traditional networks. But we've taken an approach that allows customers to be entirely flexible in the way they design their network services. So together with NEC switches, we also partner with folks like Dell to provide a data path that allows more flexibility in the kinds of solutions they deploy, but also integrate with management, security, optimization, and other applications like unified communications, so that the network becomes more than just a dumb transport, but actually has reflected in it the kinds of applications that the organizations care about. And so what we're going to show today is how we extend the protection of a Palo Alto firewall from just the perimeter of the network into the entire network. Whereas in the traditional model in our SDN network, the firewall is just at the edge of the network protecting against malicious intrusion. With this SDN approach, we can expand the perimeter to cover everywhere that the SDN network is, and then be able to enforce that policy if an infection occurs. So how does this work? So what we're going to do is we're going to have an automated policy response to an attack. It starts with the NEC controller and a set of OpenFlow switches connecting a set of hosts. And in our scenario, a host gets hacked and becomes infected. With traditional models, that host then can spread that attack across multiple hosts. But what we're going to do is we're going to integrate something we call programmable flow for Palo Alto to provide the information about potential malicious attacks into this service, and then call the API of the controller to make a change to the network. This call will make the change to the network. In the case of this demo, we're going to show how the host is actually dropping all the packets. We could have other policies depending on what the policy is for that requirement. And then that traffic is then stopped, so that host can no longer go out and infect other devices in the network. And of course, the operator gets an alert and becomes aware of the issue, can do the remediation, and bring the host back online. All this can be done today, but these manual processes get in the way of delivering those time to services, and that can be critical for how widely the infection spreads. And so really the business benefits, maybe to address the point, is really to automate and promulgate the security of the network faster than traditional networks. So we reduce the time to detect and protect the network. We minimize the attack risk because we can automate those responses. And we eliminate the manual operations so that the group responsible for security no longer has to spend their time doing this. So with that as an introduction, I'd like to introduce Sam Mita, who's going to walk us through a demo.
Hello, this is Sam. Bit chilly here, so I'm not really nervous, but I'm just cold, just to let you know. I really need to go to the bathroom after this. But anyway, so far so good, guys. I hope you enjoy here. So as Don mentioned, what I'm going to do is the Palo Alto integration enterprise security, SDN security, excuse me. So let's... please bear with me because there's a couple windows which I'll walk you through. So first of all, this is the GUI of our network controller. So I'm just gonna type it in the demo as a administrative user, and then okay. Oh, where it's going? It's moving around. Resolutions smashed.
So what you're looking at here is a view of the controller's view of the physical network. It's automatically detected all of the switches in the network, all the links in the network, and Sam has mapped the firewall into the physical environment so that we can see exactly where that is.
Okay, apologize for a little bit of technical difficulties, but so in the demonstration we have two hardware switches, which of course obviously OpenFlow enable, and then have a firewall, Palo Alto virtual appliance. This is not OpenFlow enabled, just so I just copy and paste the this device. And then beyond that, there's a FTP server, just to simulate the for the clients to download the affected traffic. Okay. And then down here below, I have two virtual machines acting as a clients, and I have a server underneath here. One of the abilities on this topology not only show detect the hardware switches, but also if I do click on the flow icons here, what you can see here is that the actual traffic is taken from A to B on which device is in the network. So this is one of the visualization on top of the physical map. Opposed to a physical map, we have a virtual map, because this is one of the unique applications running on top of our network controller, which is called VTN, Virtual Tenant Network, which we contribute to the Open Daylight community as well. So in this map, we just given the network abstracted to our controller so that we can manipulate, configure all the things from this controller. You don't need to go into the switches and things like that. That means we know what type of IP traffic, IP address or application. We know where it's coming from and going where. So that's why we can, I will come to the demo in a minute, but as soon as we get information from Palo Alto that this IP address and that packet is getting affected. So once we receive the information, we apply the policy through using this VTN network. So let me close this window moment. Now I have 5 windows actually. 2 windows on the left top. This is the one, a client. It's going to simulate get the affected traffic. And the bottom window, another client is trying to ping the same server. You might notice IP address 99.92. Top and here in the bottom as well. So basically 2 clients trying to send one single server. And the right-hand side on the top, this is an email client to receive the notification from the SDN adapter, so that the network administrator or system administrator can work with the clients which being affected by downloading the affected file. And then last but not least, this is the console of the SDN adapter that receive the information and then take some next step, which is to acknowledge and then send the policy to the controller and then give it alert to the administrator, like I said, the email notification. And then there's a action to accept the fixed actions, meaning that this client being quarantined and being reworked for to mitigate a problem. Upon that, will send the control adapter will send another action to controller to remove such a policy enforcement. As soon as that, the traffic will recover. So let's start the demonstration here. So I'm going to FTP to get the file. So there is a file called demo acre. So get demo. So behind the scene, the packets going through the Palo Alto firewall, and the Palo Alto firewall detects such malicious packets. So trying to send a message to the SDN adapter. While I'm talking here, up on the ping traffic is get lost. But the bottom client still ping is going across. If I refresh this email client, I'm being an administrator, I get an email notification. Let's check that. Okay. So Palo Alto software detected suspicious host. SDN linkage adapter drops the host IP, blah, blah, blah. Now I'm coming down to this SDN adapter console window. And I see some new dialog coming up. I'll check. So what's the next step I should make? So assuming that affected client being reworked. So I'm going to go just here. This is it says the status wait. I hope you can see it. Wait. So meaning there is some action to take. So I fixed the situation. So now I'm going to welcome this client back to the network again. So as soon as order the action, I'm fixed the situation. So the adapter will send another action to controller to allow this affected user back in the network. So as soon as that, the traffic already recovered. So that's the whole part of the automated detection. And then administrator fix the situation. After that is again automatically fix have the client back to the network without any user intervention, going to the switches, changing the echo or things like that. We do this from the linkage adapter, period. Thank you.
All right, thank you guys. So the question kind of bubbling in my head here is, what is the value of automated remediation? So if you look at the attacks that have happened over the last several years, or even maybe think of a class of attacks, what does automated remediation contribute versus non-automated remediation?
Yeah, so there's a couple different aspects. First is the ability to isolate the attacked host so that it doesn't spread across the organization. We've seen these huge attacks against POS systems, for instance, from the HVAC system. If we can isolate infected systems, then we stand a much better chance of isolating the organization. Moreover, it allows us to move more quickly so that attack doesn't spread before we have to go take widespread intervention.
Okay, and are there any numbers, say, I think in your presentation you had 85 million records that were essentially hacked last year. Are there any data points around, if this particular attack, Target or some other company, if that had automated remediation, are there any numbers that we can put to that?
Yeah, so companies are already spending $1 billion just on perimeter defense. So certainly that's, to be able to augment that is going to, be a very important aspect to their overall security posture.
Okay. Question?
Thank you very much. So for the controller, with the GUI and that, you're illustrating some of the attack, and then the administrator gets an email message. How do you envision in the future this integrating with SIEM, for example? Or do you think that the controller could be sort of a replacement for that?
Yeah, so our strategy really is to provide that network fabric and then expose that information to an orchestration system, to a security system based on customer policy. So, for instance, we're familiar with the SIEM teams that have developed their own portal. They could use the APIs to go grab the information that's going on in the network and make smarter decisions about the overall status of the network.
Thank you.
Okay, great. Thank you, guys. Thank you, NEC. Thanks for having me on. Okay, and our last contestant here is Pluribus Networks, and they're going to talk about integrated network analytics. And before Pluribus gets started, one of the things I want to point out that really excited me about this year's contestants is we didn't have one use case. We actually had a very wide, diverse group of use cases. So I think that really shows SDN, the business value of SDN, not just kind of the promise of the technology. So with that, Pluribus, go ahead and take it away.
Thanks, Jim. Hey, thank you everyone for giving us a chance to be here. Excellent. That's the kind of service you need from your software as well, basically, right? Everything just starts automatically. So, guys, one thing we are about is putting OSs on top of the switches. So these are all merchant silicon-based switches. You know, Broadcom makes it, Intel makes it, we saw Cavium making it. So various other people coming along. And what we are trying to figure out is that, you know, okay, fine, we can run switching, basically, right? We can run routing on these merchant silicon, and we can orchestrate things, and we can orchestrate tunnels, and so on and so forth. The key part that's going to make or break why people are excited about software-defined networking is not just the switching aspects and orchestration aspects, but it is like, is it opening new capabilities for us? Is it creating opportunities where none existed? Is it helping me solve problems that we couldn't solve before, right? And the whole goal here about Pluribus is that, you know, sure, we got all merchant-based boxes, you know, NetWise is running on Dell boxes. We did a couple of announcements just last week and today. We are going out on different kind of silicon and different kind of hardware platforms and so on and so forth. But the key part is it's all about creating new capabilities from your network layer, basically, right? So a few things to go about is that what is NetWise are doing, basically. Why is it so important? And you got to understand how this came about. You have a centralized controller, control plane, and we kind of know centralized doesn't work, doesn't scale, becomes single point of failure, and so on and so forth. So we'll went to distributed control plane, basically, right? And the word northbound and southbound API was invented by SDN guys, including me in there, that, you know, how do we manage northbound to the controllers or management engines and southbound to the data plane, basically, right? What ended up being is that NetWiser actually takes a slightly different approach to the southbound interface, right? So if you think of it, NetWiser is kind of a distributed OS. It's running on switch chips. It's Linux-based, and, you know, it's trying to control the switch chips and tables and program them dynamically, multiple thread, and so on and so forth, right? But the interesting part enough it does is it doesn't have a concept of a southbound interface. If you look at the switches that are coming out there, the cheapest form of the CPU complex on these switches is a quad-core processor. It has typically 4 to 8 gig of memory, even in the lowest form factor, because the world has moved to that point. Right? You go to Fry's today, the cheapest chip you're going to buy is an Intel Rangeley processor. It's a quad-core processor with full virtualization capability. And it costs you, what, $50, right? It's cheaper to buy a 4 gig memory than actually 2 gig memory. So the world has moved to the point where NetWiser can take the control plane right on the switches, right? Now, you would ask, the way to compare this is with the server world, right? When Linux runs on an x86 system, what is your southbound API there? Anyone? There is no southbound API when Linux is running on your x86 system. It's PCI Express, it's SATA, and it's your x86 instruction set. So we're following exactly the same model here. Let's integrate a distributed control plane right on the switches, basically. We call it a bare metal distributed control plane. But the entire fabric appears as an API. You know, it can be a C, Java, REST, to the controllers, which are trying to orchestrate policies and manage the system, right? The advantages here that show up is it's interoperable with any traditional network. So our boxes or NetWiser goes in, we can work with Cisco's and Arista, so you can start with brownfield deployable. It's very scalable. It's a plug-and-play fabric, basically. If you read the Dell announcement and all, it's all about plug-and-play fabric, basically, right? You don't have to go and insert wires and configure things in the box. It's all dynamically orchestrates itself. And the most important part is it converts the network from making local decisions to really distributed but centralized decision-making with a global visibility, right? So your B ports, every endpoint is visible, and we'll see that in a demo. Every flow is visible. Every TCP connection is visible. What is your infrastructure doing? What are your VMs doing? For that matter, what are your mobile devices doing? Everything gets visible here, right? And because we are sitting on top of a PCI interface and memory mapping and managing the switch chips directly, and you can mix Intel chips with Broadcom chips and so on and so forth, you don't have to worry about the security aspects of it. You don't have to worry about the attack vector that opens up just because your control plane is separated from your data plane and so on and so forth, right? The programmability is very important, basically, right? So keep in mind, SDN is really crossing buying centers, right? You are trying to run traditional switching on one side, and you are adding programmability and these capabilities on top, right? So we have a very good model here, and this is very important for SDN to become mainstream, that allows you to create the topology and let people figure out, is it L2, is it BGP, CMP, is it VXLAN-based topology, or whatever it is, separate from the programmability aspect of it, right? So if you look at the picture on your screen, basically, right, the NetOps are still controlling the topology. The NetOps are still trying to figure out how to lay the people, or people who have that expertise in that area are still figuring out the topology and the L2, L3 part of it. But then the fabric itself gets exported out to any Linux server. This Linux server can be sitting in Amazon Cloud, for instance. All you need to do is type API install on our CLI, and everything goes there, right? Including a CLI itself. So you can go and manage your fabric from Amazon Cloud. You can go and program your fabric from Amazon Cloud. Simply look at all vPorts, all endpoint, who did they talk to, what they look, and all that information becomes available to you, basically, right? REST, C, Java, Perl, Python. Of course, we are a server. Bring it on, right? This is all about your choice. The interesting part is the fabric itself. So you bring the leaf spine model. This is the driving force of SDN as well, because all these merchant silicon is enabling these leaf spine model, which is very economical for people. So you make it run, and then the interesting part is that NetWiser plug-and-play fabric actually makes it appear as a logical switch, both from programming standpoint and both from a control standpoint. And it's a very transaction-oriented. It's TCP/IP based, so you can have third-party switches in between. We don't need to have a homogeneous fabric, which is very important, right? Because nobody ever called me and said, Sneh, here's your data center. I'm building a new data center. Can you take it over? Never happened. Typically what happens is, hey, Sneh, come on here. I got these 2 racks. Can you make that run and plug into my existing network? That's what happens every time, right? So it all has to be very standards-based, TCP/IP-based, and you need to be working with existing switches and so on and so forth. It's a highly available cluster, and like I said, it's built upon TCP/IP, and it gives you a fabric-wide view and a fabric-wide programmability to go and control the network. Now, this is where the real thing starts, why we are here today, right? I'm not here to talk about L2, L3 and the orchestration part of it. We do that. We do virtualization. We do tunnel orchestration and all those. But the reason SDN Idol and you guys kind of invited us over here is, what is the killer applications here that allows us to solve a problem that wasn't solvable before, right? And this is around security and integrated analytics, basically, right? Without taps, 100% visibility, no sampling, no external taps, and dynamic threat response, and more importantly, the time machine, right? Because if you look at what is happening in your network typically, it is built around, yesterday something happened in the afternoon. I know something happened. It can be as simple as someone complaining things were not working right, and the blame goes on the network guy that, hey, your network was screwed up. Or it could be as simple as your external firewalls or perimeter defense said, okay, you got broken into yesterday, right? This is the real source of problem, because typically real-time debugging and real-time threat response, we've had that for 20-odd years. The real problem is that where go back in time and look at things and analyze them in detail to figure out what really happened there, right? Think of it this way, basically, right? This is your traditional security problem. If you look at the leaf spine pod in the middle, kind of surrounded by the red box, dotted box, and your server sitting underneath and all, that is typically a black hole, right? You typically don't have insight into what's happening in your pod, in your racks, in the east-west. This is a physical problem, guys, right? Because what has happened is in a leaf spine pod today, you have approximately 20 to 50 switches, each switching at 1.2 to 1.8 terabit per second and going bigger and bigger, right? Now, if I take those billions of packets that each switch is switching and try to funnel it to a central place to go and look and analyze it, I will need to bring a computer that doesn't exist. My analytic data structure or infrastructure will become bigger than the actual infrastructure. So what do we end up doing? We end up ignoring that. We end up putting a firewall on the northbound, and we end up putting perimeter defense around it, and we typically ignore what's happening inside your racks, basically. This is where your threats originate. This is your threat terminate, because typically a guy comes in from home, his laptop is sitting online all the time at home, he gets infected there, someone breaks into there, and he brings it and plugs into your network, and he's already inside your network, right? So that's where we need to go in. We need to go in from a sampling-based approach to really a full 100% visibility-based approach. It's not going to happen with a central system. The way NetWiser solves this is with really a distributed big data approach. Each switch becomes a big data engine. Each switch NetWiser instance is gathering all the data at 100% visibility, collecting the metadata and centralizing it, and we'll see that in the demo, basically, right? So the real part here that happens is that we eliminate all the tabs and the separate visibility fabric. We get into 100% monitoring, not sampling-based. It's 100% visibility, and we get into the dynamic threat response. Keep in mind, the second bullet, the monitoring 100% of visibility, having access to that data, being able to see that thing is the critical problem we are solving here in this particular scenario. There have been a lot of work done for 20-odd years to make threat response happen, analyze the data, and do whatever is needed for. The problem was access to the data. How do I see what's going on, right? This is really the problem NSA is trying to solve. This is really the big guys are trying to solve. How do I see all the data and get the right data? The switches have TCAM. You can set hardware-based flows with NetWiser. So you get the data into the software that every single packet is useful to you. You're not sampling, you're not discarding 90% of the packet because they're junk. You're getting all useful packets. And from there, you're analyzing them locally and correlating that information and sending it to the central tools, basically, right? And so on and so forth. And of course, we work with all third-party tools and whatever, firewalls and analytic IDS, DPS agents to kind of go and analyze the data and actually use our flow capability to take automated response on them, basically, right? So having enough said, let's jump into the demo quickly. And again, the world is built around two things. Keep in mind, we are straddling the boundary of the old guys and the new guys. So what we did in NetWiser is we have a full CLI, we have a full UI, right? And full APIs. So I'm going to go and show you some stuff on the CLI very quickly. Then we're going to go into the UI and have a look at the same information on what higher level things can do, right? So unlike, I don't have a prepared demo, guys. Typically, we run at Pluribus in Palo Alto. Our entire network runs on NetWiser. It's been like that for 2+ years. We just log into there and we start trying stuff. So bear with me. It's entirely possible that someone is, although I did send an email, please don't upgrade the software while I'm doing a demo. But, you know, you'll meet our guys. They're crazy. So just very quickly, and we have had some issues with the resolution here. So let me see if I can. And I apologize, guys, for whatever reason. I think someone really need to do a startup on how to get these screens up at the right resolution in these conferences. So you know, you go from something like a MacBook Retina display to a 1024, and it's really not. I hope people can read it in the end, but it's a bunch of switches in PNFab. They're all working as one logical switch, and I can log into any switch. It doesn't matter. It's a plug-and-play fabric and full peer-to-peer, so it doesn't matter which switch you log into. The interesting part is, and just for the sake of time, I'm going to just focus on the analytics side of things, right? When we type something as simple as connection show, basically, what you're going to see is every VM, every server that's running at Pluribus networks, their IP, who do they talk to, what kind of port they are running on, what kind of service it is, what is the state of the current TCP connection, how many bytes in, how many bytes out, and all that kind of information. 100% visibility. If the connection is not visible here, it's not going through our network at least, right? And this is, again, nothing is being terminated on the switch. We're not talking about we are a switch in the between, right? So nothing is being terminated here other than my SSH session. Everything is really between VM to VM or server to VM or whatever, right? I mean, so the interesting part that starts happening is, to give you a flavor of connection show, I can do something as simple as sort descending on total bytes, and I can say, limit output to 5. What I want to do is look at my 5 biggest users on a per switch basis, right? So we hit enter, and what we immediately start seeing is that Aquila 2, PNLab 01, what are the biggest users there? It looks like HTTPS, someone transferred 3.27 gigabyte worth of traffic. That was 3 hours, 44 second back, basically, right? We have some connections here which are 50-day old, basically, right? Part of the reason is we have beefed up our switches with more memory and whatever, so we can go back months. By general, it depends on what is your load and how many, what kind of appliances or switches you're deploying there, right? So typically, your mileage will vary from few hours to few days to months, right? But the interesting part here is that, you can actually go and slice and dice this in any which way you want, and you can say, what I want to see is within last 10 minutes. So you can very quickly go and say, okay, show me what is within last 10 minutes. And you're starting to see the real-time data there, right? You can actually go and say, okay, this guy right here, let's look at it, Command C. And what I want to do is show the source IP, and we want to see every single connection that this guy issued, basically, in its lifetime. We can see every single server. Seems like it talks to only one server. We can go back as far as we want, but it looks like it's really just talking to one server, basically. So you can go and look at this guy and okay, I want to see who else talks to the server. Maybe there's something going on here. So you can go and say very quickly, dest IP, sorry, and we look at this server, and we can start seeing all the clients that talk to it. So this is a legitimate server, seems like it's our NFS server that I picked up, and multiple clients are talking to it, and so on and so forth. We can actually go back and look at, okay, let's look at the start time yesterday. So we want to see 2015, maybe month is 06, and we want to see 15th. Yesterday, between 10 a.m. and 11 a.m., what happened, basically, because we feel like someone attacked this or this server was broken into. So we can go and look at data at that time, basically, right? And sorry, guys. And what we are seeing is yesterday, between 10 a.m. and 11 a.m., every connection that was established was served. So notice that we converted this from a black box, the entire network, has been converted from a black box to 100% visible. Everything that's happening in my infrastructure, I have got it up here, basically, right? And obviously, I can use my vFlow API to take action, drop, block, anything, and automate that through my REST API or C API or Python API. But the part I also wanted to show you was the user interface to this, basically. So all your top users are visible here. You can actually go and click on this guy and say, okay, show me all the connection issued by that server. That's visible here. You have full visibility into your how many VNets, VLANs, VXLANs, and so on and so forth. Obviously, if you're dealing with security and compliance, I need to be able to audit my own system as well. So we can go into the transaction side of the house, basically, and we can look at every transaction that people are doing. So you can see, you know, we did a vFlow delete operation. There's a blocking flow, probably a demo happening in our booth here. We did a vFlow create, and you know, these are all Fabric transactions that are all visible here, and so on and so forth, basically, right? You can also go and look at the entire topology that is being built based on the analytic visibility with switch, with server. You can actually go and say, okay, I want to go and look at a particular link here and see all the flows on that link, and you kick that, and immediately same information that I was showing you with CLI is now visible here, basically, right? Everything is kind of live here through GUI. And the goal here is, again, you know, if you look at the SDN standpoint, and if you want to make it palatable to different people who are using networking and security, you need to have all these tools to fit in, basically, right? And the big power here is that the switches are now becoming programmable, so you have the ability to run applications on the switches itself, right? Both NetOps and DevOps can coexist on these switches and offer new functionality capability to people, right? And on that note, basically, I think, you know, we will take some questions. And I mean,
so there's this whole new body of data that you've now made available to these security tools. Are they capable of handling all this information now, or do they choke on that huge amount of data?
Jim, why do you ask me a hard question? My previous guys got easy questions here. The part is that the industry is changing and adapting to the new capability that's coming out. We ended up building a lot of our big data analytic capability primarily because industry wasn't there. So some case we are generating all the data, we had opened up the network, and we realized that people are not ready to use it. So we ended up building that application. By the way, the application makes us more money than the networking application or orchestration application. And then the APIs are now being plugged into the ecosystem. So, you know, we have some of the firewall company, Fortinet, for instance, now is starting to come and use this. Radware was there yesterday till late night, trying to go and pull information out from these SDN fabrics and actually build their automated response system on top of that. So industry is starting to come along, basically.
Great, and clearly there's forensic value right out of the gate here. So let's thank Pluribus and Sune. And one more hand for all of our contestants today. Thank you, guys.